an AI-generated post for your viewing pleasure. Revolutionizing robot mobility. The future of locomotion control with contact condition policies. Imagine a world where robots glide through complex environments with the grace and agility of a human. Traditional control methods often hold them back, restricting their adaptability and performance. But a groundbreaking new approach to locomotion control is on the horizon, a method that could redefine how robots move and interact with their surroundings, vastly expanding their capabilities. Before we dive deeper into this fascinating research, let's take a moment to consider what it is that makes robot locomotion so challenging. This is where the concepts of locomotion policies, model predictive control, and behavioral cloning come into play. Stick around, and I'll clarify these terms, ensuring you're all set to follow along as we explore the intricacies of this revolutionary work. In a world where we increasingly rely on robots for assistance and automation, understanding how these machines can navigate human environments is crucial. Researchers Michal Ciebielski and Majid Khadiv have made significant strides in this area with their innovative paper titled Contact-Conditioned Learning of Locomotion Policies. Their work not only challenges conventional robotic movement techniques, but also sheds light on how robots can achieve versatile and resilient locomotion, managing multiple gaits with seamless transitions. As robots are deployed in complex and unpredictable environments, ensuring their stability and adaptability becomes vital. This new study presents an intriguing solution, conditioning locomotion control policies on contact locations and timings, instead of the traditional velocity-based methods. You might be thinking, what does that even mean? Well, simply put, it allows robots to be more aware of their interactions with the ground, enabling them to move more effectively across varied terrains and situations, much like we humans do. Now, let's break down a few core concepts that will help you understand the significance of this research. First up is locomotion policy, which refers to the guiding rules that dictate how a robot moves, effectively functioning like a roadmap for its movement. In traditional systems, these policies have often focused on average velocity and direction. Then there's model predictive control, MPC, a sophisticated technique that generates movement strategies while accounting for various constraints, ensuring that the robot operates within safe limits. Lastly, we have behavioral cloning, which is a method where a robot learns from an expert's movements, essentially imitating what it sees. By conditioning their techniques on future contact points, Ciebielski and Khadiv aim to enable robots to navigate challenges intelligently and confidently. Now that we're all set, let's uncover the technical details of this novel approach. So now that we have a foundation, let's dive into the technical contributions of this research to see how the authors advanced our understanding of locomotion control. The core idea of the research revolves around contact condition policies, which condition the locomotion control of legged robots based on when and where their feet make contact with the ground. Unlike conventional methods focused solely on velocity and direction, this approach allows robots to better adapt to diverse terrains and dynamic environments. In essence, it mimics how we humans adjust our steps based on the surfaces we encounter. What's particularly groundbreaking is the validation of a single policy capable of generating multiple gaits. This means robots can efficiently transition between different walking and running patterns without needing individualized controllers for each gait. Instead of relying on cumbersome algorithms that break down when faced with unexpected situations, these contact condition policies offer a more generalized solution to locomotion challenges. The research demonstrates that contact condition policies significantly outperform velocity condition policies, not just in traditional task execution, but also in adapting to unforeseen challenges. The authors analyzed failure rates and agent survival times, finding that this new policy framework ensures robots are far less likely to tumble or falter, especially when navigating through rugged terrain or when they need to adjust quickly after disturbances. This performance alignment showcases how contact conditioning helps robots exploit shared structures between different gaits effectively. However, while the authors present compelling results from simulation experiments, They do not sufficiently address the computational limitations and practical challenges of implementing these policies in real-world scenarios. The paper acknowledges that state-of-the-art constrained nonlinear model predictive controllers, NMC, generate whole-body trajectories for a given contact sequence, but they also highlight the computational expense associated with these approaches. This raises an important question. How do contact condition policies help alleviate these computational burdens when transitioning from simulation to practical implementation? Moreover, the results section focuses on simulation experiments without adequately addressing the feasibility of scaling these approaches for real-world use. The paper does not discuss how the proposed methods would handle the myriad of factors that can affect locomotion in uncontrolled environments, such as varying terrain, unexpected obstacles, or changes in the robot's physical condition. As robotics continues to evolve, understanding these practical implications will be crucial for the successful deployment of advanced locomotion strategies in everyday applications. Now that we've explored the technical aspects, let's discuss how this research fits into the broader landscape of robotics and what it means for the future of motion control. This research is a significant departure from prior work that primarily focused on reactive control, and it brings together concepts from both imitation learning and model predictive control. The authors employed behavioral cloning that draws from expert controllers, a technique that's simple yet powerful. This marriage of traditional control methods with learning-based approaches helps overcome the common problems associated with reinforcement learning, such as overfitting and the high sample cost involved. By illustrating the limits of velocity-based conditioning and demonstrating the power of contact as a goal representation, the research aligns beautifully with current trends aiming to incorporate more nuanced and flexible control systems in robotics. As we see applications aiming for greater adaptability and efficiency in robotics like autonomous vehicles or drones, this method could influence strategies across various fields requiring locomotion, opening doors to even more remarkable applications down the line. Additionally, as the paper hints at, future work may involve applying this technique to quadrupedal locomotion and humanoid manipulative tasks, which could lead to even more sophisticated robots capable of handling complex real-world scenarios. However, the paper does not sufficiently explore how these contact condition policies would perform under varying environmental conditions, which is critical for real-world applications. If these policies cannot effectively adapt to real-world challenges, their utility in diverse robotic applications may be limited. This realization not only showcases the potential of these advancements, but also raises the bar for what we expect from robotic systems in our everyday lives. Understanding how to implement these policies in diverse contexts is crucial for advancing robotic locomotion capabilities. The implications of these revolutionary contact-conditioned locomotion policies are profound. They embody a significant leap toward more resilient and flexible robotic systems capable of tackling unpredictable environments and tasks. As we venture into a future where robots play an increasingly vital role in our lives, the ability to achieve seamless, multi-gait locomotion will be crucial for a variety of applications, from everyday personal assistance to emergency responders. This research by Siabielski and Khadiv is not just about robots taking steps. It's about them stepping confidently into the future. What are your thoughts on this new technique? Could we be on the verge of revolutionizing robot mobility as we know it? Share your opinions in the comments below. If you enjoyed this video, please give it a thumbs up, and don't forget to subscribe for more fascinating insights into the world of robots and artificial intelligence. Until next time, keep exploring the incredible possibilities of technology around us.